Let's take a look at a lot of the properties that exist in substances because of these intermolecular forces. One property has to do with boiling point and vapor pressure. That's a topic in and of itself, so that's going to be covered in a separate video. We're just going to look at solubility, viscosity, surface tension, adhesive and cohesive forces, and phase changes within the context of this particular lesson. All right, when we look at solubility, you should remember from your prep class the edict of like dissolves like. And when we talk about like dissolves like, what we're looking at is similar intermolecular forces interact well with other similar intermolecular forces, okay? And so when I say like oil and water, they don't mix with each other because oil is solely dispersion forces, whereas water is predominantly hydrogen bonding. Water will mix well with something that's polar because it's also highly polar, but water doesn't mix well with things that are nonpolar and have no hydrogen bonding, okay? But if I have two things that both hydrogen bond, they're going to be, have a higher, chance of success in interacting with each other. All right, so when I look at substances, things with similar type of intermolecular forces will dissolve in each other. All right, and so what we're looking at is in a pure sample of something, we have let's say we have a solvent. We have solvent-solvent interactions. If I'm trying to dissolve something into that, I have solute-solute interactions. So when we have a solute that dissolves in a solvent, those solute-solute interactions and solvent-solvent interactions are replaced by solute-solvent interactions. And so we have to have forces that are comparable in strength in order for that to occur. Okay, so we have our solute, and solvent, that then get replaced by solute solvent. Okay? All right, so when we look at some of these solubility rules, okay? Polar solvents dissolve what type of molecules? Polar or nonpolar? Polar. All right? Nonpolar solvents are going to dissolve nonpolar molecules. And then if I have molecules with the polar and nonpolar ends, they will be frequently soluble in both polar and nonpolar solvents or neither polar and nonpolar solvents. They'll frequently be soluble in both because they have one end or the other. Okay, and then my head blanked out my blank here, but I can write it underneath. Polar solvents are good for solubilizing salts. Okay. All right, so when we look at that solubility, all right, here I've got, methanol. Methanol, hydrogen bonds, okay, and water, which hydrogen bonds. So if I mix methanol and water together, they're both small, they're both polar, they both hydrogen bond. Should they interact with each other? Absolutely. And so we see the solution of methanol and water, where now I have hydrogen bonds interacting between the methanol and the water. When I look at solubility, and I look at solubility in water versus hexane of a series of alcohols. Now hexane, okay, we've got all these carbons. Oh my goodness, so many carbons, so many hydrogens. All right, so hexane is a straight chain hydrocarbon. It is nonpolar. All right, and so when I look here, if I look at methanol, it's the smallest alcohol. It is infinitely soluble in water. Now, the infinitely soluble, this is miscible. Okay, when two things are infinitely soluble in each other, they're miscible. Okay. All right. So that single carbon doesn't have a lot of dispersion forces in order to interact with the hexane. But once I get to ethanol, I only add one more carbon. All right. It's 2 carbons. It's still miscible in water, but now it's also miscible in hexane. Because what's happening is we have these two ends. I've got my nonpolar carbon side chain, and then my little polar head, that's the hydroxyl group on the alcohol. So this end is polar, and this end is nonpolar. And I see that with all of these. Okay, and as we increase the size of that carbon side chain, we start to lose our miscibility and then our solubility overall in water, because by the time I get to hexanol, I have 6 carbons, okay? Just like hexane, 6 carbons. So that carbon side chain, this is so small up here that we can get a little bit of interacting with the water, but not a whole lot, because that carbon side chain gets in the way. That's taking up the bulk of the molecule. So even though overall hydrogen bonds are a stronger intermolecular force than dispersion forces, once that carbon side chain gets too long, our ability to access that little polar head that hydrogen bonds goes down. And so we lose that solubility in water. Okay, so, all right, so we can ask some questions here. Which of the following pairs are miscible, i.e. infinitely soluble in each other? All right, well, when I look at water and ethanol, we just saw on the previous slide, these were miscible. Okay, all right, now we can take a look at hexane and xylene. Okay, so again, hexane, we've got all those carbons. Now xylene, okay, we have this going on where we've got this ring, and then we've got hydrogens, okay, and then again, the hexane will have all the hydrogens around it. I don't want to draw out all of those hydrogens all over again. So the xylene, do you think it's polar or nonpolar? It's nonpolar. And it's a similar size to that hexane. It's a little bigger, but it's a similar size. So it's nonpolar. So do you think they're miscible or not miscible? Yeah, should be. All right, now we're going to use some deductive reasoning here, okay? So we're going to take some facts that we know and see if we can piece this together. So now we're going to look at our ethanol and the xylene. And again, this right here, this is the xylene. Okay, so let's see what we know. And then this is ethanol. We know that ethanol and hexane are miscible. Okay, we saw that information. We know that. Okay, we suspect that hexane and xylene should be. Okay. Therefore, do you think ethanol and xylene should be miscible? Yeah, by that type of reasoning, ethanol and xylene. Okay. All right. So those should be miscible. Now, viscosity. It's resistance to flow. So here's a concept. If a liquid has strong intermolecular forces, then particles will not flow past easily, and viscosity will be high. Okay? All right. So here I have a picture of two liquids. I have a green liquid on top and a red liquid on bottom. Which one is the most viscous? He said the red one. You are correct, right? Because you can see the red one has barely flowed out at all. When we look at a bunch of these straight chain hydrocarbons, as the chain length goes up, so does the viscosity. Because remember, the larger it is, the more points of interaction it has. And so that viscosity is going to go up. Okay? When I look at the viscosity of water, what's happening with temperature? Well, as temperature increases, viscosity goes down because it thins out. This is why it's really important in your car to have the right viscosity of oil, because when your car is running, what's happening? Well, it's running at a high temperature. And so oil, as you're pouring it in to refill your oil, might seem unnecessarily thick and viscous. Well, as your car heats up, it's going to thin out. And it's important to have the right viscosity because you don't want your gears to grind together, nor do you want it to be so viscous that they stick together. Okay, so viscosity does decrease with temperature. All right, now when I look at surface tension, all right, we've got these intermolecular forces that are going to affect things differently depending on where the molecule is. And so when I have a molecule in the interior, it's attracted by others on all sides. But molecules on the surface only have others on the side and below them. And so they feel this net attraction downward. All right, and so we get this net attraction downward because they're not being acted on by anything on top. And so they'll move into the interior to increase the attractions and become more stable on all sides. And then a liquid surface tends to have the smallest possible surface area. All right, and so it behaves like a skin covering the interior. And so when we look at things, we can see crazy things with surface tension. Like this is liquid mercury. Liquid mercury, the force that's involved in liquid mercury is metallic bonding, an intramolecular force. And so it very much only wants to interact with itself, so it balls up. Unfortunately, we can't show this anymore because they don't let us have liquid mercury in labs. We used to have liquid mercury thermometers even at home. That was how my parents took my temperature when I was a little girl, was with mercury thermometers. And if one dropped and broke, the mercury spilled out. And we used to play with it because it was really cool because it balled up on the countertop. But liquid mercury has really high surface tension because it is so attracted to itself that it actually balls up away from whatever surface it's on. We get some interesting things with surface tension. Depending on playing your forces right, you can actually sometimes get paper clips, or some countries have metal coins that are light enough that you can actually float them on water. I've never managed to do this, but I've actually had a couple students that managed to get paper clips to float. It's a matter of balancing that surface tension so you don't get that pull downward, all right, and getting it to float. Water bugs, they can walk on water both because the surface tension spread out and because their legs are coated with things that hydrogen bond, so they interact with the water and so they stay on top of the water. Okay, when I look at different substances, I can look at those forces and I can look at the surface tension. So when I'm looking at diethyl ether, okay, diethyl ether is polar, but it's got, those oxygen or those carbon side chains on either side of it. So it actually has two major forces. It has dispersion for those carbon side chains and the dipole because it's got a net dipole moment up toward the center. Ethanol, its major force is hydrogen bonding. It has a little bit higher viscosity than our diethyl ether. Butanol has hydrogen bonding, but it has a very significant carbon side chain, so it also has very strong dispersion forces. So the combination of both of those being strong is why butanol has a slightly higher surface tension than ethanol does. Water, what's its major force? Very strong hydrogen bonding. Okay, And then when I look at mercury, okay, remember mercury, its major force is going to be its intramolecular force, the metallic bonding. And so that one's going to have the highest surface tension because those bonding forces, they're going to trump our intermolecular forces anytime. So the intramolecular forces are absolutely stronger than the intermolecular forces. Okay? All right, we can look at surface tension. All right, so in orbit, there's no gravity pulling on anything. And so if water escapes in orbit, it's spherical because it will come in on itself because it's going to reduce, that area on the outside. And so we have to think about two different things going on here, things called adhesive forces and cohesive forces. All right. So our adhesive forces, attraction, if I can spell, between liquid molecules and the surface of the container. And then cohesive forces are attraction between the molecules in a liquid. Okay. And so when we look at adhesive and cohesive forces, if something spreads out or something balls up, it's a war between those adhesive forces and cohesive forces. What's stronger, the attraction between the molecules in the liquid or the attraction between those molecules and the surface they're on? And so we can see, capillary action, like with water, or we can see this balling up, like with mercury. And so here we've got, that forming of the meniscus. And here we get the opposite. It's going the other way. All right. And that's because in water, we have stronger adhesive forces. And in mercury, we have stronger cohesive forces, because the silicon dioxide in glass, that can hydrogen bond. The oxygens can hydrogen bond with the hydrogens in water. But in mercury, there is no hydrogen bonding. The only thing the mercury is attracted to is itself because of the metallic bonding. And so it doesn't interact with the walls of the test tube at all. And so it balls up on itself and has stronger cohesive forces. Okay. All right. And then we have capillary action. What is capillary action? The ability of a liquid to flow against gravity up a narrow tube. Okay? And so we've got this attraction of the water to the glass, like I just explained, it draws the water up the side. It was really interesting. Years ago, I had this craft kit, and it had these little dye pouches, and I didn't finish using everything, and I wanted to go back to it later. And so I didn't want the dye to spill out, so I put the dye in a Ziploc bag, standing straight up, and then I taped the Ziploc bag to a wall so it would stay, standing straight up. Well, there were definitely some attractions between the dye packets and the dye itself because I forgot about it. I got busy and it was behind a door, so I didn't notice it for a while. Until one day I looked behind the door for some reason and I had dye pooling at the bottom of the Ziploc bag because there is this capillary action. There is a strong adhesive force between the dye packet and the dye, and it crawled up the dye and then it started spilling out, or the dye up the packet and started spilling out. So me being the scientist that I am, I left it, and sure enough, after a certain amount of time, the dye actually started climbing up out of the Ziploc bag, and then I finally took it down because I didn't want dye spilling out all over the floor. So these adhesive forces can be really interesting. Okay. All right, and then phase changes are simply the ability to go between our three different phases of matter. And so you should have learned these terms in prep chem. So if I go from a solid to a liquid, I'm melting, a liquid to a solid, I'm freezing, solid to gas is sublimation, etc. So these terms you should know already. When we look at our phase changes, we've got an enthalpy involved with each phase change. So if I'm going between gas and solid, that's our delta H of sublimation. If I'm subliming, it's positive. If I'm doing the opposite process, the deposition, it's negative. So same amount of energy, just opposite sign, depending on what we're doing. Sublimation takes energy, deposition gives us energy. Okay, vaporization, delta H of vaporization for liquid to gas, and delta H of melting between our solid and our liquid phases. Now, when I look at the energies here, okay, here, all right, I'm changing a temperature and I'm still within a phase. But here, my temperature stays constant, but I'm undergoing a phase change, all right? Here, I stay within my phase, but I change the temperature. And here, my temperature stays constant, but I'm undergoing a phase change. Because once I hit the melting point, once I hit the boiling point, at that temperature, the phase change starts to occur. And so it continues to take an energy at that temperature to cause the phase change. So why is the line for going between solid and liquid so much smaller than the line between going from liquid to vapor? Well, this has to do with understanding these intermolecular force attractions. The delta H of vaporization is a lot larger than the delta H of our fusion, because if we look at this picture here, this is just doing the same thing opposite. What's happening when I go from a solid to a liquid, right? Well, that solid just starts to move around. But has it gotten really far apart from each other? No, they're still really close to each other. They're just moving close to each other. But when I start to go from the liquid to the gas, now, instead of being right next to each other, they're far apart. And so it takes more energy to go between the liquid and the gas, because we're not just disrupting those tethers, we're breaking them. It goes back to, pulling my camping trailer. As I start to tow it, how much pressure do I need to actually break the tether? Well, if I'm towing my camping trailer, I don't want it, that tether to break. But if I'm going between a liquid to a gas, I'm breaking the tether. I have to have enough energy to overcome the energy of the attraction between the molecules. And so the stronger the attraction, the harder it is to break, which is why water has such a high boiling point, because water has 4 simultaneous hydrogen bonds. It has a very strong attraction to itself. And so I have to disrupt all of those hydrogen bonds, get those tethers to break to get water to go from the liquid to the vapor. All right? Hopefully this was all a review. Just FYI, every single one of these slides that we just looked at are the same exact slides that I used for my prep chem class. So I went through it a little bit quickly because this is supposed to be a refresher, not brand new. But if it is, you're going, okay, go through it again, read the textbook. You should always read the textbook anyway. All right, and again, if you're struggling because you're trying to remember this and you've got some clarification questions, that's the perfect time to come see me in office hours. All right, now next we'll talk about vaporization and boiling point. We're going to put that into its own little category together. All right, that's next.